Hello everyone, I am Alper Selver from Dokuz Eylul University, Electrical and Electronics Engineering Department. And today I'm going to talk about evaluating the performance of machine learning methods at biomedical image processing applications. So, as we all know, the AI tools are increasing in capacity, in success, in accuracy, in several applications. Now, as the number of AI tools are increasing, their state-of-the-art results for the applications they are being used are getting better. But their generalization is still poor, and the clinical integration is rare. So in this talk, I'm going to try to talk about the reasons why this is happening and how do we overcome these problems. Now, the discussions in this presentation will be based on a very recent article on COVID-19, and this article investigates the common pitfalls of machine learning methods to detect and prognosticate COVID-19. So although this article is specifically prepared for COVID-19, it really underlines several important aspects that should be considered by AI developers in order to obtain clinically usable medical approaches. Now, the important thing that is focused by this article is that there are 2,212 studies which use chest radiographs or CT scans to detect COVID-19 from these images. And after an initial screening, the authors have reduced these 2,212 studies to 415. Now, this is a significant reduction at the initial screening, and they use a checklist to do that, and we are going to discuss that checklist. What are the reasons to reduce these studies to 415? And then they made a quality screening, and after the quality screening, the number of articles is reduced to 62. We are also going to discuss this quality screening, and after the systematic review of these 62 articles, they have concluded that none of the models identified are of potential clinical use due to the methodological flaws and/or underlying biases. And this is stated as a major weakness given the urgency with which validated COVID-19 models are needed. Now, although this article discusses COVID-19, we know that these results, these warnings, are applicable to other applications as well. Now, this problem is not really specific to academical research studies. It is also a problem for industry. And in this article, this is also a very recent article, 100 commercially available products are investigated together with their scientific evidence. You can find those products at ai4radiology.com, and when these products are analyzed, it is found that 64 of 100 products lacks the evidency of peer review and real quality check. And these 100 commercially available products are all CE marked. So only 18 of 100 AI products have demonstrated potential clinical impact. So this report states that the artificial intelligence in radiology is still in its infancy level, even though already 100 commercially available products are available. So this is a very important point that should be investigated, why these products are lack evidence to perform successfully in their clinical areas. During the commercialization process, the people who are usually engineers and expert clinicians, they are also asking these questions to themselves. So here at Stanford University, Human-Centered Artificial Intelligence Center, they are discussing as being the producer of these products that are medical AI devices evaluated properly. So they stated as an abstract, many devices were tested solely on historical and potentially outdated patient data. Now, when we are talking about AI or machine learning, the data becomes very, very important, and the use of data, as it is stated in many talks, in many discussions, very few of them are reflecting the real clinical settings. So these discussions now play a very important role on the development of AI-based systems. Now, our discussions will include two AI systems, actually two subgroup of AI systems. The first one is what we call the classical machine learning approach. It's the artificial neural networks. In the artificial neural networks, what we are doing is we have an image and we are extracting features from it. Now these features, there are various features that we can extract. For example, the histogram and the histogram properties like the skewness and the distribution and the kurtosis, or the convolution-based features like all kind of filters and textures. And once we extract our features, we are using a dimension reduction and feature selection techniques to obtain a more representative set of features. Now, this is a very important step because when you extract features, you add a dimension into your solution space, and if this solution space have very high dimensions, and these dimensions are linearly dependent, then your model can have problems in the performance or in the generalization capacity. So to prevent these, we use dimension reduction or feature selection. Now, once we apply this, we use the input to our artificial neural network, and we use a hidden layer or layers, depending on our application, and we get an output. So, for example, here our output is a liver with lesions and other clinically important regions painted by the algorithm or found by the algorithm. Now, this is called the conventional or classical machine learning approach, and what is now is a hot topic is the radiomics. And radiomics is actually simply repeating this procedure for a specific region of interest. Now, for example, if we consider this breast lesion case, when the image is acquired, there is a ROI, the region of interest. It is drawn over the image, and this ROI represents our clinically important region. Now, this region can be manually extracted, or you can use this artificial neural network pipeline to obtain this region. But once this region is extracted, several features are obtained from it. For example, the tumor intensity or tumor texture. And once this feature extraction is completed, these radiomics features can be combined with clinical features. And here, like neural network we have shown in here, a neural network or another statistical analysis can be employed to obtain the result. Another example is on MR imaging, and here is a brain lesion segmentation approach. And once the region of interest is extracted with segmentation or manual labeling, several features are extracted. So here shape features are extracted through morphological operators, textural features are extracted, and space frequency based features are extracted such as wavelet, and statistical features are extracted using the intensity transformations like histogram that we have seen in the previous example. Now, once we obtain this set of features, again we use feature selection or dimension reduction to obtain a linearly dependent feature set that has a lower dimension and a more efficient representation capacity. Now, afterwards, a statistical analysis is performed to determine if this is a low risk tumor or a high risk tumor. Now, if your results are statistically significant, then you can simply use these features to make a diagnosis or to follow the prognosis. And in the deep models, on the other hand, we use the image as the input directly, and we let the network produce the output. Now, the interesting point here from the optimization point of view, that deep models have more hidden layers compared to artificial neural nets. And in these hidden layers, actually before the hidden layers, features are extracted internally by the deep models. Now, they usually extract much more features than we extract in the artificial neural network case. So how this results with an increased accuracy, because we have said we need to use dimension reduction or feature selection to obtain a more effective result. This is an currently unanswered problem from the optimization point of view. So many simulations are being performed, and at these simulations the experts conclude that at a higher dimensional space with a very high number of local minima, the stochastic gradient descent algorithm would end up eventually in a good result. So here is a controversy between artificial neural networks and deep models, but still this doesn't change that deep models are performing much better compared to the artificial neural networks in general. Now, back to our common pitfalls article on COVID-19. This article, as we said before, analyzed 62 articles, and 2 of these articles use hybrid models. 37 of them use deep models, and 23 of them use classical machine learning tools. Now, why these 2,000 papers or 2,000 research studies are reduced down to 62? Now, this is because of a checklist for artificial intelligence in medical imaging. The authors of the Common Pitfalls article have used this checklist published by Radiology Artificial Intelligence very recently to eliminate the articles that do not complete or that do not comply with this claim checklist. Now, this checklist includes several items. For example, here, the quality screening failure reasons. For example, in 61% of the papers, how the final model was selected is not given, and the method of preprocessing of the images is not given in 58% of the articles, and the details of the training approach are not given in 49% of the articles. So these are all eliminated since these information is not included in the article. And the remaining papers that are analyzed for detailed investigation, 29 of them did not complete any external validation, 30 did not perform any robustness or sensitivity analysis of their model, and 26 did not report the demographics of their data partitions. 25 didn't report the statistical tests used to assess the significance of results or determine confidence intervals. 23 of them did not report confidence intervals for the performance, and 22 did not sufficiently report their limitations, biases, or issues around generalizability or generalization. Now, this list continues. I just included some important ones, and there is also a smaller list about this issue, which is called minimum information about clinical artificial intelligence modeling, the MI claim checklist. Now, as researchers who wants to conduct research on AI for medical devices or for medical imaging, the researchers, I think, must read this checklist claim, which is the current which currently lists all the necessary steps that should be carried out to conduct an AI research and make sure that nothing is missing in this checklist. And also another important point is the risk assessment tools. And we know that one of the biggest risks is the bias of our data or the bias of our model. Now, this COVID-19 article evaluates the risk of bias by using a tool called Probast, which is a tool to assess the risk of bias and applicability of prediction model studies. Now, the article found that participants' predictors, outcomes, and analysis bias, which creates 4 domains for bias analysis. They found that 55 of 62 papers had a high risk of bias in at least one domain. So to prevent bias, which is a very hot topic, which is being discussed in several talks, you should be checking Probast tool to prevent bias in your data or in your model or in your outcomes or in your analysis. Now, one of the biggest issue is the data amount, reliability, and validity. And again, in this COVID-19 article, the data sets considered in 2 categories. One of them is the public data sets, and the other ones are the private data sets. Now, the private data sets are impossible to check, of course, and these private data sets mainly include, as you can see, China, France, Iran, United States, Belgium, Brazil, Hong Kong, and Netherlands. And here are the list of the public data sets. Now, the public data sets play a very critical role in the development of AI-based systems, because the researchers can use these public data sets and compare their algorithms in this application area with the other researchers who use the same data sets. This is becoming a standard approach for making research. However, there are very important points on these data sets that should be considered. For example, many papers give very little attention to the source of the images. And this results with source issues. For example, 16 of 62 papers that are selected for review used pneumonia datasets of Germany as a control group. However, they commonly fail to mention that these datasets consist of pediatric patients aged between 1 and 5. So, as you can see, for a system to check adults with COVID, you are using a model or you are testing your model with a pediatric patient dataset. Now, pediatric imaging is a completely different radiographic technique, so it is not feasible to check your model with a pediatric dataset unless you are specifically design your model with pediatric datasets. So developing a model using adult patients with COVID-19 and very young patients with pneumonia is likely to overperform as it is merely detecting children versus adults. So what it is doing is just to differentiate children and adults rather than specific sickness detection. And another problem is the Frankenstein datasets. And the Frankenstein datasets is due to the issue of duplication and source become compounded when public Frankenstein datasets are used. And this means that your dataset is assembled from other datasets and redistributed under a new name. For example, in this COVID-19 article, one dataset combined several other datasets without realizing that one of the component datasets already contains another component. So you are internally increasing, doubling, tripling the number of images that is obtained from a specific center or obtained from a specified condition. So this of course creates an important bias for your model. Now, another source of bias is the implicit biases. The images uploaded to a public repository and those extracted from publications are likely to have implicit biases due to the contribution source. For example, it's likely that more interesting, unusual, or severe cases of COVID-19 appear in publications. The Turkish Radiology Society have very important talks about these topics, about the prevalence and bias, and I hope you will have a chance to listen to them. And also RSNA, the Radiological Society of North America, has important talks and panels and discussions about these implicit biases. Now, still the grand challenges is becoming the prominent tool for making a biomedical image processing application or imaging application using the AI models. For example, for this COVID-19 case, RSNA just announced an AI detection challenge. And in this challenge, the data is prepared based on the discussions that we have followed from the checklist. So let's discuss more about these grand challenges, which is the new trend for the for developing AI systems. Now, the process of developing an AI system for a medical problem, and here specifically for the image processing problem, we first collect data, and the important part is to label them. So regarding the radiological image processing, there are three kinds of labeling, and then after labeling, we need to determine the evaluation strategy. Now, when we are labeling, if we have a classification problem, then here is a nice example with cats and dogs. If you have a classification problem, then what you need to do is just to say if there's a cat or not. So this is kind of an easy labeling. And if what you want to do is to localize it, then you have a classification plus localization problem. Then you use a bounding box to locate the cat. And if you want semantic labeling, if you need a semantic labeling, then what you need is to really isolate the object. Here, cats and dogs, and the duck is isolated. Now, this is the object detection problem, is also very popular, for example, for pedestrian detection in nowadays for industrial problems, and it is also very popular in medical image processing. Now, the evaluation strategy is totally related with the labels. Now, if you have a classification problem, then you need to use some accuracy metrics like the area under the curve and so. If you have a classification plus localization label the problem, or an object detection problem with multiple objects, then you need additional evaluation metrics such as the ones that are pointing out the false positive, because in most of the problems the real challenging case is to eliminate the false positives when you are collecting the true positives. Now, the evaluation strategy should consider two steps. The first step is to use quantitative metrics, and the second is the qualitative analysis like the expert opinion. So here expert opinion is highly related with, again, labeling, because inter and intra-expert variations determines the upper limit of your accuracy or of your success. So you are not usually trying to reach 100% of success rate in terms of quantitative metrics, but you are trying to reach inter or intra-expert variability level to call your model a successful model. And the fourth step is algorithm development. It was all before. Always the algorithm development plays the key role, of course, for the model performance, but the grand challenges now allow us to go online without any algorithm development. So currently, the first three steps, collecting data, labeling, and evaluation strategy, makes the 50%, the half of the solution of the problem. So if you create this data collecting, labeling, and evaluation strategy determination processes, then you can use grand challenge websites to make this data, labeled data, available to all the research groups that are interested in the world, and they can use their models to solve your problem. So without any algorithm development stage, you can find a solution, an effective solution to your problem, or with algorithm development, you can directly compare your algorithm results with other people in other countries. Now, grandchallenge.org is a good example for hosting grand challenges, and it currently includes more than 200 up-to-date grand challenges that you can attend. In Turkey, we have finished a grand challenge. It is called chaos. It's the combined CT, MR, healthy abdominal organ segmentation challenge. And we have recently published it in Medical Image Analysis Journal. So if you have a look at this article, it consists of a tremendous amount of statistical analysis because as you can see in the map, there are more than 1,600 participants who has participated to this challenge all around the world. So there were more than 500 submissions, and it's a big deal to analyze these submission results. By the way, the grandchallenge.org also allows you to create automatic evaluation process. You code your metrics and integrate it to your website. So when anybody from any place in the world submits a result, the website automatically evaluates it based on your metrics and publish it on the leaderboard. So this is an ongoing process, an online process where any research team can attend anytime or can send results anytime and get instant feedback from it. So this is a huge accelerator for the research studies. But even so, the 98% of all models that is sent to chaos among 500 submissions is based on UNet. So 98% of the results used a modified version of the UNet. So you can see how concentrated these research studies and how they are compressed in a single model. Even though there are many research teams, we are using a single tool to obtain the results. Now, chaos has 5 different tasks. It includes, for example, cross-modality learning. This is about learning CT and MR together. So previous studies mostly concentrate on individual modality, like you learn your machine learning algorithm learn on computed tomography and perform on computed tomography and reach a success level, and the same applies for MRI. But using cross-modality learning is a challenging step, and it is important to have ongoing research challenges, the image processing challenges, or whatever your application is, to keep everything updated and to receive new results and to analyze them continuously. So this is a huge work. Now, since such challenges dominate the field right now, there are also articles which are investigating how transparent is the reporting of these results. So the question is, do the winners change if we change the chosen metrics and their combination method? As I said before, for example, chaos is using 5 different metrics to analyze the results, and it combines them by simply averaging, but there are also other methods. Now, if you have a look at this publication, you can see that 70% of all biomedical image processing applications concentrate on segmentation. So this is a huge ratio, and even this is a simple task. The segmentation is a well-known, well-established task. Depending on your application, your evaluation method should change, and it is in most of the time a single metric like a dice coefficient or an F1 score or the accuracy level is not enough to represent your results. Now, considering this, the MICAI Society, Medical Imaging and Computer-Aided Interventions Society, published a review article in Medical Image Analysis again. It is called BIAS. It's about transparent reporting of biomedical image analysis challenges. Now, this bias statement aims to improve the transparency of the reporting of a biomedical image analysis challenge, regardless of the application, image modality, task, or category. And it also presents a checklist which authors of biomedical image analysis challenges are encouraged to include in their submission when giving a paper on a challenge. So, as you can see, again, we turn ourselves into a checklist and a guideline which should be completed before attending a challenge or organizing a challenge. So now, as you can see, we are always talking about the checklists and the guidelines because there are several parameters and several issues that needs to be considered for creating a healthy data set, evaluating it correctly, and analyzing the results in a good way. Otherwise, there exist many pitfalls that limits the applicability of the AI. Now, we are also organizing another challenge that's called the VILA challenge, the vessel extraction and extrication of liver analysis. So in this case, we also have very rigorously annotated hepatic and portal vessel trees, and you end up with a very complicated vessel tree at the end. This takes a lot of time, especially for the radiologists who needs to use a software to make it perfectly clear. But as you can see here, there are still some disconnected labels and so in the reference data set, but this is in the nature of the process, and also in other applications. For example, in lung vessel analysis, you have these problems. So this is unavoidable because of the limitation of the image acquisition process. You should also consider this, and the review articles also consider these shortcomings of the labels for the reference standard, and even though your algorithm can overperform in such cases, for example, your algorithm can find these vessels incomplete, and since your reference is not complete, since it's broken, it can give you some wrong results, like you have done something wrong. So you should also update your labels. The labeling process is also not a static process. Based on the results you have received, based on the analysis you have received, you need to update your labels as well. And another issue about labeling is the weak annotations. Now, this is a relatively new concept. For example, on the left-hand side, what you are seeing is our VILA challenge annotations. This is a rigorously annotated data set. And reds are hepatic veins, and blues are the portal veins. And on the right-hand side, you see another kind of annotation that is from PAVES challenge, the peripheral artery vein enhanced segmentation challenge. And this is a challenge that is organized by 31st Society of Magnetic Resonance Angiography Congress. And why this is called a weak annotation? Because this is not annotated by manual labeling. Instead, the organizers use different MRI sequences and obtain their fusion to create weak annotations. Now, weak annotations is of course does not have a high quality as rigorously annotated manual annotations, but the good thing is you can keep obtaining these weak annotations. You can continuously obtain the weak annotations because as you acquire images from different sequences, you get more and more images, and you can increase your data set continuously without paying for labeling. And if this is done correctly, then you will get an almost or theoretically infinite number of data in your data set. This is the perspective that should be followed on creating data sets, because even though you spend a lot of time to collect your data, to collect images, to annotate them, at the end of the day it becomes outdated at some level, or people will lose interest if you do not change the test set due to the peaking problem. The peaking problem is something like overfitting, you can say. It is not overfitting because it is based on test data sets, and the reason behind is in the challenges, multiple submissions are always allowed. So you send the result to a challenge, you obtain a score, and then based on your score, you modify your model. So the training set does not change, but based on your result on the test data set, you are changing your parameters. And when you change your parameters based on your score in the test set, you are actually making an internal overfitting, which is called peaking. And this really limits the generalization capacity of the deep models or machine learning techniques at the end of the day. Now, there are two important points here, as stated. The first one, both deep models and artificial neural networks training performance, of course, depends on the training data quality. And the second is, on the evaluation side, the model revisions rely on test data quality and test data variations. Now, the outcomes of this talk is, if we follow AI guidelines, we can improve our data quality, our machine learning methodologies, the repeatability of our results. We can remove or at least reduce bias significantly, and we can improve our generalization capacity. So even at COVID-19 case, which is discussed on the right-hand side in this common pitfalls article, so none of the reviewed literature reaching the threshold of robustness and reproducibility essential to support utilization in clinical practice. And this is due to poor quality data, poor application of machine learning methodology, and poor reproducibility and biases in the study design. So the biggest problem in nowadays is not to design a deep model architecture. Many of the research teams cannot do that and use techniques like transfer learning to modify an already trained model to obtain good results. And since we cannot do much on the model level, what we need to do is to go to the source of the problem and to improve the data quality when we are collecting the data, and labeling quality when we are creating our targets. And if we do that very carefully by following the checklists and the guidelines presented in this presentation, you can obtain a healthy data set that can be used for quite long, and that can be used to generate models that have really a robust performance and a nice generalization capacity. Now this is a local journal, Science and Technology, and a 2015 July issue. Here is a question. Sorry, this is in Turkish, but it is artificial intelligence, a threat or a chance? So if we are careful when designing our AI tools in terms of data quality and evaluation strategy, it's a luck. And we know that AI now is an integral part of our routine clinical work, and it's an integrated part. It will be an integrated part of our medical devices. So when we are designing it, we shouldn't shortcut these important steps. We should be as transparent as possible. The accuracy, the quantitative evaluation metrics all by themselves does not tell much things about the real success rate of our model, but instead we should follow the checklists. We should follow the guidelines when designing our model. So thank you very much for listening, and goodbye.